Hello everyone. Today I will present my paper published in Wireless Communication Letters. The name of the paper is Static Intelligent Metasurface for Task-Oriented Semantic Communications. I will present it from five aspects: background, systems model, problem formulation and solver, simulation results, and conclusions. I will first introduce the writing background of this paper. In semantic communication systems, the joint optimization of the semantic encoder and channel encoder usually increases the transmitter's training costs and the difficulty of deployment. Specifically, the figure on the left shows a conventional deep learning-based semantic communication systems, where the deployment of the transmitter's background knowledge base semantic encoder and channel encoder brace three challenges, including high deployment costs, high training costs, and high inference costs. To address these challenges, we proposed a SIM-aided semantic communication systems and verify its feasibility. Recently, SIM emerged as a promising technique for realizing fast and efficient wave domain computation, which can reduce the cost and energy consumption of training and inference. In addition, the SIM consists of multiple tightly static metasurface layers, each of which consists of many low-cost meta items. Moreover, the SIM can be deployed in front of the transmitting antenna. Against this background, we examine an image recognition task-oriented semantic communication systems leverage a SIM. Then we introduce the systems model. As shown in Figure 1, the systems task is an image recognition task. Moreover, the number of the metal atoms on each layer is referenced by n. The total sequence of SIM is referenced by d, and the number of layers of SIM is referenced by L plus 1. At the receiver, M antennas are arranged in a uniform nearly array, and each receiving antenna corresponds to an image class. Moreover, the input layer of the SIM serves as a digital to analog converter to map the image source to the input layer, and the rest of the layers of the SIM construct an electromagnetic neural network, which serves as a semantic encoder to transform the signal passing through the input layer into a unique beam towards the receiving antenna. In a contrast to conventional communication, the transmitting antenna in all systems, including source encoding and semantic encoding, the source encoding is referenced by Z0, and the semantic encoding is referenced by B. The ZL is the transmission coefficient matrix, where amplitude AL and phase phi-L is as follows, and the W is the propagation matrix, which obtained by the Rayleigh-Sommerfeld diffraction theory. In addition, we adapt the Ricci-Fallin model to model the wireless channel H, where LP is the path loss and K is the Ricci factor. HLS is the non-offsite complement characterizing the direct path between SIM and the receiver, and HNLS is the non-line of sight complement. As a result, the signal received by the receiving array is modeled as Y, and the antenna with the maximum energy selected can be modeled as M hat. Then we introduce the problem formulation and the solver. To train the SIM to steer the wireless signal towards the corresponding antenna, we let the QM denote the expected probability distribution, and the normalized received power is replaced by Y tilde. The cross entropy is used as the loss function to measure the power pattern across the receiving array and the expected probability distribution of recognizing the input image. The problem of minimizing the loss by jointly optimizing AL and phi-L is formalized as an optimization problem, denoted as P1. Specifically, the L is the objective function, the Ym is the received signal at the M antenna, the B is the EM response of the SIM, the ZL is the transmission coefficient matrix of the L layers, and the AL and the phi L is the individual amplitude and phase shift constraint respectively. To solve P1, the amplitude AL and the phase phi-L of metal atoms in each layer are initialized, and then the partial derivatives are calculated. Next, the AL and phi-L are updated. Then the AL and phi-L are normalized, and finally, the convergence is judged. Output AL and phi-L if convergent. Otherwise, repeat this process. Then we present the simulation result of this paper. Here we illustrate the system's parameter set by the simulation in this paper. We first illustrate the recognition accuracy under different numbers of L and N. As observed in the figure on the left, the recognition accuracy using the SIM increased with L, thanks to the enhanced inference capability of the multi-layer diffective architecture for achieving more accurate beam steering. Besides, the figure on the right shows the recognition accuracy increased with N as more metal atoms effectively enhance the representational capability of the SIM. Furthermore, we illustrate the recurrence accuracy under different values of DSR and M. The figures on the left shows a short propagation distance would improve the recurrence accuracy, as the smaller values of DSR would cause less path loss and more distinguishable channels. Besides, the figure on the right shows the recurrence accuracy decreased as M increased, as recognizing more digital requires the SIM to accurately focus multiple bits on an increased number of receiving antennas. Finally, we make a conclusion of our presentation. Specifically, we proposed a SIM-aided task-oriented semantic communication systems where the transmitting antenna transforms signals into a uniform beam towards a receiving antenna corresponding to the image class, and SIM was utilized to perform short encoding and semantic encoding in the wave domain. We formulated an optimization problem to minimize the cross-entropy, which measures the difference between the power pattern across the receiving array and the expected probability distribution of recognizing the input image. To this end, we used an efficient mid-batch gradual descent algorithm to train the transmission coefficients of SIM's metal atoms to learn the semantic representation of the image. Extensive simulation results verify the effectiveness of utilizing the SIM for image recognition task-oriented semantic communications, achieving more than 90% recognition accuracy. We put the reference mentioned in this presentation at the end for reference. Thank you for listening.